right, welcome back to physics. This video is for Thursday, Friday morning time. And we are talking about different types of forces. So let's just recap really quickly. What were some things that we learned about forces from doing the PhET simulation and the reading on Monday, Wednesday? Things that we learned. A force is a push or a pull on an object. For example, I can push, I was going to say I can push my little brother down. Like, that's awful. But you know what I mean. I could also pull him back up because I'm kind. Okay, so force is a push or a pull. Whenever there's an interaction between two objects, there's a force upon each of them. When the interaction stops, though, the two objects no longer experience the force. All right. All forces have strength and direction. So if you're looking at kicking a soccer ball, you need to consider how strong are you kicking it and in what direction are you kicking the soccer ball. We also talked about how an unbalanced force is what's needed to cause motion. There were two scenarios in which we consider unbalanced forces. An object that is at rest will go into motion if it experiences an unbalanced force. Also, an object that is currently in motion that experiences an unbalanced force can change its speed or its direction or both. And what comes to mind with that scenario is like a car collision, right? If you're driving a car and then you're hit by another car, that's an unbalanced force, and it's going to change your speed, your direction, or both of them. The last thing that we took into consideration with forces is that some scenarios are going to have balanced forces where they are equal and opposite. And if that's the case, then they cancel each other out. No motion is caused, but it is important to remember that those forces are still there. It's not like they just disappear or there aren't any. It's just that they are equal and opposite and they cancel out. So that's kind of a recap of some things that we learned about forces. What we're going to tackle today are the following questions. How can we categorize different forces? How can we measure different forces? And what exactly are the different types of forces? Now, at this point in the lesson, you have a job to do. You need to go open up the types of forces notes. They are on Google Slides, and you're going to fill them out wherever you see a purple star like this one. So, for example, I went ahead and opened them up on mine. This very first slide on slide number 2 has the purple star in the corner. That means that you are responsible for filling it out while I go over it in the video. All you have to do is just type, whatever I have on my slides. Same thing for slide number 3. Again, you see the purple star. So you have to fill out the descriptions for each of those forces. Same for slide 5, 7, and 9. You do not, I repeat, do not need to fill out slides 4, 6, 8, or 10. Okay, also do not hit submit on these notes since we're going to be finishing that up in the afternoon time. All right, so let's get into it. The very first question, how can we categorize forces? There are 2 different categories of forces. The first category is a contact force. The word contact means that 2 things are touching each other, and if that's the case, then there's a contact force between them. So, for example, you are walking your dog and you are holding onto the leash and you feel the pull from the dog and you're pulling on your dog. There is a force between you and the leash. The second type of force is an action at a distance force. This results when 2 interacting objects are not actually touching each other, yet they are somehow still able to exert a push or a pull. Think about all of the stuff that we learned from first semester with like positive and negative charges and electric forces. That is action at a distance force. Or more commonly, thinking about how a magnet works, you can put it nearby something that's metal, and if it's close enough within its magnetic field, it will be drawn to it or it will be repelled by it. Those are action at a distance forces. So at this time, hit pause if you need to copy down those definitions. Now, some examples of those forces. Contact forces, remember 2 things have to be touching in order for there to be the force. Things are forces such as friction, tension, what we call the normal force, air resistance, what we call an applied force, and a spring force, like within a spring. Those are all contact forces because 2 objects have to be touching each other. Examples of action at a distance forces include gravity. We don't actually have to be touching things for gravity to work. electrical forces, like what we talked about in first semester with attraction and repulsion, and same idea with magnetic force. So again, hit pause if you need to at this point to copy down those examples of categorized forces. So each of those forces we're going to go over, but we're going to go over them in 4 different scenarios. You have these 4 scenarios on your notes. So after each one, you can hit pause, copy down some notes, and then we'll move on to the next one. So the first scenario, we have a water bottle that is at rest on a table. So what are the forces that are at play there? Because there's definitely contact between the water bottle and the table. Why aren't they moving? The 2 forces that are present include gravity. Notice that we use the what is that called? Like the shorthand F and then subscript grav. Okay, so it's a force of gravity. That is the force that occurs between 2 massively large objects. So in our case, gravity comes from the Earth and then the sun. And so gravity is the force that pulls all of the objects on Earth towards its center. I hope I described that right. We'll go over it again in class. So gravity is pulling the water bottle down onto the table. The other force that is at play is what we call the normal force. Whenever you have the force of gravity and it's pulling the water bottle down onto the table, equal and opposite is the normal force, which is pushing up on the water bottle. That's why the water bottle doesn't just go like kaplunk through the table and down onto the ground, which would be so wild to see in real life. So normal force, F norm, or the normal force, is the support force exerted on an object that is in contact with another stable object. That was kind of an awful description. Anyways, pause if you need to, otherwise let's move on. The next scenario, now we have the water bottle. It's laying down on the floor and we are pulling it across with our hand at a constant velocity, which means same speed, same direction for however long we want. In this case, the motion is going towards the right, so we are pulling it towards the right. So what forces are at play, considering that the water bottle is in motion? There are 3 of them that are coming into play. The first one that I actually want to talk about is the blue arrow. The blue arrow is called the applied force. You might see it written as F-app. That is the force that is applied to an object by a person or another object. So the fact that this person's hand is grabbing onto the water bottle and is pulling it, that is called the applied force. The forces that are opposing the applied force include this pink arrow, which represents air resistance, also known as F-air. That is a type of frictional force that acts on objects as they travel through the air. Think of an airplane, think of a hot air balloon, all those different things that happen in the air, right? Air resistance is when an object is running into air molecules. Another force that comes into play is friction, F and then F-R-I-C-T, the force exerted by a surface as an object moves across it. So in this case, the floor is adding friction against the water bottle. The force of friction opposes the motion of the object. So if the water bottle is moving to the right, the force of friction is going to the left. There are 2 kinds of friction force. There is sliding and static. So as an object is legit moving across a floor or another surface, that's called sliding friction. Static friction is the reason why my cup can stay on the table and not just like randomly go sliding off somewhere. Static friction is staying in one place. All right, the next scenario is we have a water bottle that is being pulled across the floor at a constant velocity by a rope. All right. A little bit different than the scenario before. The main force that I want to talk about in this scenario is what's called tension force, or F and then T-E-N-S, force of tension. This is a force that's transmitted through a string or a rope, a cable, or a wire when it's pulled tight by forces acting from opposite ends. So if you can imagine, this rope is being tied to the water bottle. On the other end, it's a person who's holding onto it and is pulling it. Within that connection there, within that rope, there's tension force. It pulls equally on the objects on opposite ends, okay? So that's why we use a double-headed arrow to represent it. That force goes both ways. The last scenario is this. A water bottle is being pushed down on a spring by your hand. Such a wild scenario to imagine. But just like the tension force, the spring force is kind of similar. We use the notation F spring. The force is exerted by a compressed or a stretched spring upon any object that is attached to it. So, if you can imagine you have a spring and you've compressed it as much as you possibly can, that would be considered like a large spring force. If you were to compress it just a little bit, we would say it's like a little bit weaker of a spring force. Or in the opposite way, you can think if you stretched that spring and you were to let go, right, it would bounce back. Again, the amount of force is proportional to how much you've stretched it, like a lot of force or like a little bit, or like, same thing if you compressed it. That's the spring force. All right. Notice double-headed arrow as well. All right. The last little chunk here, how can we describe forces? You're going to see this pop up quite a bit, especially as we use simulations and such. When we talk about forces and we talk about units for forces, we're going to be using what's called the Newton. It's represented by a capital letter N. Yes, it is named after Isaac Newton, the famous guy who had the apple fall on his head and then like magically he came up with the idea of gravity. There's more to that story than just that, but you get the gist. When you see it written as like 10.0 N, we read it as 10 newtons of force. All right. So at this point, if you need to rewind or do whatever you need to do to get those notes filled in, go ahead and do it. Otherwise, if you have everything filled out, then you are all set for this afternoon.